Okay, so now we're going to be taking a look at equilibrium applied to acid-base systems as well as solubility systems. So we're looking here at acid-base equilibria and also solubility equilibria. And there are a few things that we would not need to make sure that we brush up on as we enter this section. So the things to recall would be determining pH. So using the pH equation, using Henderson-Hasselbalch, etc. We'd also need to recall all of the skills we learned with our equilibrium systems. Okay, and specifically manipulating your equilibrium expressions. The use of ice tables, etc. Okay, so we're using a lot of the info we used in the previous sections now to address equilibrium applied to acids, bases, and also solubility. The first thing we're going to take a look at here is something called a common ion effect. Up to this point, what we've been looking at are systems where we have a solution containing a single solute. Now we're going to be taking a look at properties of a solution that change when a second solute is introduced. So in order to address this, we're going to be taking a look at Le Chatelier's principle, which applies to systems at equilibrium. And when those systems are stressed, how does the system respond how does the system respond to that stress? Adding a reactant or a product can be thought of as a stress to that system, as we've seen previously. So here we have an example of acetic acid, a weak acid. So we know we can write the equilibrium expression or the equation for that. We can set up our ice table. You have initial concentrations. Let's say we have a 0.1 molar solution to begin with. None of the products, as this reaction proceeds, we will lose a certain amount of the reactant. We will gain the same stoichiometric amount of product. And then at equilibrium, we have our concentrations. We can write our Ka expression for this as we know how to do, maybe in our sleep at this point. So we have our H plus times a CH3 COO minus divided by the concentration of the acetic acid. Okay, we can make our approximation that this here is going to be equal to 0.10. So we're approximating X is small. We solve for X there and we'll see that it's 1.34 times 10 to the minus 3. So the pH of that solution then would be 2.87, right? That's something that we know how to do. We've done a lot of it in the previous sections. What would happen if we added a salt, such as sodium acetate, so NaCH3COO, to this system, right? Sometimes this is written as CH3COONA. So we put the cation at the end. And that's just to show that this being a salt, we have a sodium ion in place of a proton there at the end. So we know that salts, this is our salt, will dissociate. Our assumption here is that our salt will dissociate completely. We're going to get Na plus, and we're going to get the acetate ion, CH3COO minus. So if we added some of this, guess what? We're actually adding some of the acetate ion, which is an ion that is common, or that is already present in our system. Okay, it is already present on the product side over here. So if you add a salt, right, that salt will dissociate in solution to give us a sodium and the acetate ion in this case. So the anion is that common ion that we are referring to. It's common to the equilibrium system that we had to begin with. So what that means is if we're now adding some of the stuff on the right side, so we're adding products, something to the right, this then, according to Le Chatelier's principle, will drive this equilibrium to the left, right? So it forces the equilibrium to the left side to use up some of that, or whatever that added acetate ion happens to be, right? And this This all has to do with Le Chatelier's principle, again, because we're starting off here with our equilibrium system. So the equilibrium then is actually driven toward the reactant or to the left side. Okay, so by adding that common ion, we shift the equilibrium to the left. So when we add some of the acetate ion to it, right, in order for this to shift to the left side, what this means then is what will happen afterwards is that the system will consume some of the acetate ion that was added, but it will also consume, in order for this reaction to go from right to left, we also have to use up some of the H plus. Right? And if we're using up some of the H plus, this then will lead to a change in the pH. Because the pH is the negative log of the concentration of the H plus. So we can expect something to happen to our pH, right? If we add that common ion, in this case, we start off with a pH of 2.87. As we add some of the acetate ion, as you can imagine, if we're consuming some of the H plus concentration is going to decrease. If the H plus concentration is decreasing, that means it's becoming less acidic, it will become more basic. So we can predict then that the pH in this instance should increase, should become more basic as the H plus concentration decreases, right? Because it's being used up as this equilibrium is forced from the right to the left. So we haven't done any calculations right now except our initial ice table. We're just qualitatively looking at what should happen if we added that common ion. So let's take a look at a specific example of one such system. So it says determine the pH at 25 degrees Celsius, prepared by adding 0.05 moles of sodium acetate, right? So this is our CH3 COONA to 1 liter of a 0.1 molar acetic acid solution, assuming that the addition of the sodium acetate doesn't change the volume. Right? So volume is constant. All we're doing now is adding some of this stuff to the system. So we can set up our ice table to begin with, right? Initially, let me highlight what we have here in green. Our initial conditions are 1 liter of a 0.1 molar acetic acid, right? So the concentration of this to start with is 0.10 molar. And then initially we have none of this stuff. Now we're adding some of the acetate ion. How much are we adding? We're adding 0.050 moles. To this, and that's in how much volume is added to 1 liter. Okay, so the concentration there would be 0.050 molar of the acetate ion. Remember now, this salt here, the sodium acetate, the CH3COONA, right, that will dissociate completely in aqueous solution to give you the anion and the cation. So everything here is in a 1-to-1 mole ratio. So whatever number of moles we start with of this thing is equal to the number of moles of that thing, right? That's why we can make that that equality, because everything is in a 1-to-1 mole ratio. So initially, we have our concentration of the acetic acid, and we have our concentration of the acetate ion, right? So as this reaction proceeds, right, we can predict then what is going to occur in this case, right? We're going to, again, use up some of the reactants. We're going to lose X amount of the reactant. We assign that as X. And we'll lose that. We're going to gain the same amount, stoichiometric amount of the products. So we have 0.10 minus X at equilibrium, X for the H plus at equilibrium, and 0.050 plus X at equilibrium for the acetate ion. So when we substitute our values into the equilibrium expressions, now remember, our Ka is equal to the H plus times the CH3 COO minus divided by the CH3 COOH. Okay, so we know what the Ka is. We can look that up. Right, that is 1.8 times 10 to the minus 5. And that is equal to now the H plus concentration, which is X, times the CH3OO minus, which is 0.050 plus X, and that's divided by the acetic acid 0.010 minus X. Okay, so we're going to make our assumption, assume X is small, and we're going to check that assumption at the end as well, which you should always do. So then we end up with this being equal to X times 0.050 divided by 0.010. That's 1.8 times 10 to the negative 5. So we solve this for X. Okay, I'm not going to go through the math. I think we can do that on our own. So we end up with X being equal to 3.6 times 10 to the minus 5 molar. So then the pH, remember now X here is the concentration of the H plus. So then the pH would be the negative log of that. And that gives 4.44 as the pH of this solution that has a common ion dissolved in it. And because that forces the equilibrium to the left side, the H plus concentration decreases. We expect the pH then should increase, right? So originally, just with the acetic acid, it was 2.87. Here we see that the pH has gone up to 4.44, right? So the answer does make sense. When we've applied this new idea of the common ion effect to the system, we're going to see this again when we get a little bit deeper into this section.